This cycle, you already probably have come across this, called the Carnot cycle. This would be what you may call the ideal cycle. This is a cycle, it will be the best possible cycle if there are no irreversibilities. No irreversibilities internally or externally. So let's look at first at the heat engine and say that this is a cycle and it takes energy from a reservoir at temperature TH and a quantum of heat which is QH, and dumps QL into the low temperature reservoir, and the difference of these is W. So the first law is obeyed by this system. So we are safe on that. And we say, what is the highest possible efficiency that we can get from this? And that tells us that there has to be a relation. Firstly, there should be no irreversibilities. No reversibilities inside the system. So there could be a pipe flow, there could be a turbine, there could be a compressor, there could be a cylinder piston arrangement, whatever is there inside. There should be no irreversibility inside this. The second thing is, this heat transfer, this is going to be the cause of external irreversibility. That means when this heat is being transferred, it will do so to some device in this system. And we are saying is that this heat transfer should be reversible. For that to happen, the temperature of the substance here should be TH minus a very small amount, so that we have reversible heat transfer. And second, when this heat transfer is taking place, the system is undergoing some process there. The temperature here should be TL plus a very small amount over there. And that is leading us to the idea that for heat transfer to be reversible, the temperature difference should be very small. And so if this is approaching zero, this temperature is almost equal to this temperature. And we say this is reversible heat transfer. And since the temperatures were same, we can say that this is reversible or isothermal heat transfer. So it sounds a little bit funny in that how can a heat transfer take place if it is an isothermal process? Isothermal means there is no heat transfer, but heat transfer means there is energy transfer. So recall that this is now only an approximation that we are doing, that the temperature difference takes place over an infinitesimally small difference. That's all. So this has to be a reversible heat transfer process. Same thing here. Reversible isothermal, we can add both together. Reversible isothermal heat transfer, and this is also reversible isothermal. So if all these conditions are met, then we look at the efficiency of the Carnot cycle, the cycle efficiency. This will be as before W upon QH, which was 1 minus QL upon QH. And we can go through an involved derivation and show that the maximum possible efficiency, which is the Carnot efficiency, this is 1 minus TL upon TH. Or if we looked at it in another way, we apply Clausius inequality on this, then what happens is, it is telling us that cyclic integral of delta Q by T, this is QH is positive divided by TH plus QL is minus QL, heat out of the system, divided by TL less than or equal to 0. And so the Clausius inequality is telling us that if this were to be equal to 0, then QH upon TH should be equal to TL upon TL. So in case this equality is 0. And you can see that this leads to this, this is QL upon QH is equal to TL upon TH. Then we got this efficiency. So what I had just stated, we can actually prove it very simply by employing Clausius inequality. And we invoke the fact that the most ideal cycle is going to be a reversible cycle. So we put this equal to 0 and went ahead. Now the Q's and T's in this are the system Q's and T's, the temperatures here. But because this was isothermal heat transfer, the fluid here, the working substance here, is at TH very, very slightly less, and here at TL very slightly more than TL. But we are approximating both as TH and TL, which is why we got this number. So we got a very important expression which tells us that the maximum possible efficiency you can get is determined by the temperature of your high temperature reservoir and by the low temperature reservoir. It is independent of what type of a cycle you make, how many stages you make, what working substance you have, how small it is, how big it is. None of that matters. Only these two temperatures tell you what is the maximum possible efficiency that you can get. Okay, so let's play with some numbers on this and say, what sort of numbers are you looking at? So we say that, look, in the real world, when I have to make electricity, which is what your work is, I have to have a high temperature source and I have to have a low temperature reservoir. So we need to figure out two things: a high temperature reservoir which we shall call a source, and a low temperature reservoir which we will call sink. So those two things are there, and we want to work with what is around us. So we say, well, what is the sink that is around me? And you have either in nature, you have either the water in the oceans or air in the atmosphere. They are the only two things we have naturally occurring. One can argue that, well, I will reduce my temperature of the sink by putting a refrigeration plant. Well, yes, you will put that plant, but in trying to reduce the temperature, you will consume a lot more energy. And that way, although your efficiency of the heat engine went up a little bit, the overall efficiency is falling. So that's not a very practical solution. And we say, well, what type of temperatures do we have around us? And we say, look, in winters, there are some parts of India where temperatures are -10, -20, -40 degrees Celsius. And in summers, we get temperatures of the order of 55 degrees Celsius in some parts of the country. And water, well, depends on if you are looking at the ocean, you have temperatures which are ranging of the order of 23, 24 degrees Celsius. So that's the type of sink temperatures that we have. And this expression tells us that to get highest efficiency, TL should be as low as possible, TH should be as high as possible. So let's say, well, where should I locate my thermal power plant? And the answer would be go to the place which is very cold. And that probably means the Siachen Glacier. Well, it's way too far off. Getting any material over there is a challenge. Putting it together is a big difficulty. And then even if you make electricity there, how are you going to get it out? So all of this make it infeasible. Although scientifically it is possible, technically it is infeasible. So we don't do it. And so we put it somewhere, and the power plant I just showed you the picture, that is at Vizag. And Vizag takes water from the ocean at 23-24 degrees Celsius, and it's a coal-fired power plant. So the source is sort of a furnace in which we are all the time continuously burning coal. So what we are doing is we created a big space in which we continuously keep firing coal and air. It keeps burning, and as this heat is transferred to the water, we keep firing more and more coal. So this temperature remains elevated at temperature TH. Same thing we do if you are firing oil in a boiler to produce steam. And the maximum temperature we can get in this case is of the order of, say, about 1100 degrees Celsius, somewhere over there. If you burn very good quality coal, you could get 1700 degrees Celsius. So which means that if you burn very high quality coal, which we don't have in our country, what we have is very low quality coal with a lot of ash in it. Even if I get good quality coal, we get a source temperature of about 2000 Kelvin and a sink temperature of the order of 300 Kelvin. And now we put it back in that thing and say, well, what is the best efficiency I can get? Then you get that for these temperatures, the Carnot cycle efficiency becomes 1 minus 300 upon 2000, which is equal to 1700 by 2000, which is 85%. A nice high efficiency. We'll be very happy to get that. In the real world, the power station you saw would be lucky to get to 45%. So this is what is theoretically possible. This is what is actually there. All our electricity comes from plants whose thermodynamic efficiency is of this order. But now we look at another way to analyze this problem, because here we assume that the furnace temperature was 2000 Kelvin, and so the water temperature that it produced was also 2000 Kelvin, which is what we assumed in the Carnot cycle. But that's not really the case, because as this transfers heat to the water going in, the maximum water temperature we have there is 565 degrees Celsius. So this you can say is of the order of 800 or let's say 850 K. I'm approximating it. And in this case, the efficiency now becomes 1 minus 300 upon, say, 800. And that is 500 by 800, which is about 62%. So we sacrificed something because we could not operate the power plant whose steam temperature was 565 degrees Celsius. There is very little we can do with the ambient. So we've said that, okay, the best I could get is 62. In fact, this 300 will also be slightly more. It's about 310, 315, 320. That refinement one can do later on. That's not an issue. But it's of the order of like 60, 62%. So with 60, 62% possible, theoretically, practically, 45% is what we get. So what it tells us is that in this system, whatever energy we took from here, some of it came out as power, some went over here, and in this particular case, if the work output was say 500 megawatts gross net, then it tells us that this is only 62% of what we put in. So in reality, we are putting 500 divided by 0.62. This is how much QH is there, and the difference of these two is QL. That means in this case, instead of 45% coming, 45% came out of the electricity. Where did the 55% remaining go? And that went as QL. It was dumped into the atmosphere. And how we did that? We just took lots and lots of water from the ocean, condensed the steam, the water temperature rose by about 10 degrees Celsius, and we threw this water back into the ocean. Or we did that with water and we cooled the water in air, so that heat was transferred to the air. So if this was 500 megawatt electrical output, we are dumping of the order of 500 megawatts into the atmosphere after burning 1000 megawatts from the fuel. That's what the total energy balance looks like. That's a huge amount of energy which we dump into the sink. And we have to do it. That's what the second law of thermodynamics is telling us. Okay, so let's take some other example now. There's a lot of talk of solar energy now. So sun, as we know, is at 6000 Kelvin. And the atmosphere is at 300 Kelvin. Then clearly this ratio tells you that we can get great cycle efficiency by going to 6000 Kelvin. But that means that your working substance also has to go to 6000 Kelvin, and that is not possible because neither we have a substance nor a metal or a material which can withstand 6000 Kelvin. So we work at much lower temperatures. So solar thermal, what one ends up doing with some of the pictures which I had showed you in first module, where you concentrate the solar rays onto a point and heated the steam, there we got temperatures much like the fossil-fired power plant, steam temperature of the order of 550 degrees Celsius, sink again 300 Kelvin or thereabouts, and so the efficiency of solar thermal power plant in the best case is comparable to the efficiency of a coal-fired power plant. If this temperature were to be lower, the steam were to be generated at 300 degrees Celsius, efficiency would further come down. In a nuclear power plant, the reactors that we have, fission type of reactors, they produce steam at about 300-320 degrees Celsius. So that is 573 Kelvin, and that is your TH. And your dumping back TL is still 300 Kelvin. So if you look at the ratio now, the thermodynamic efficiency will be 1 minus 300 Kelvin upon 573. So this is 273 upon 300. And so this is about less than 50%. No, sorry. TL is 300K, this is 573, and this is 273. This is of the order of, this comes out to be a very large number there. No, wait, there's something missing here. Okay, the efficiency of a nuclear power plant is of the order of 28%. The temperatures are much lower. And you can also look at the idea of ocean thermal. Where The sea surface temperature is 23 degrees Celsius, and at 300 meters depth, the temperature is like 12 degrees Celsius. So theoretically it is possible that this is used as TH, this is used as TL, and we can see what type of efficiencies we can get. Very, very small efficiencies is what we get here. So that's the idea of what sort of numbers we are dealing with here. So that's all coming out from what the Carnot cycle was. We'll take one more example, then we'll stop, and that is the gas turbine. When the first gas turbines were made in the 1950s, the maximum temperature in the turbine was of the order of 700 degrees Celsius, and efficiencies were very, very low. And then they realized that if we can take this up, the engines will become more and more efficient. And this has been the big driving force of much of R&D in aircraft engine design. It's still continuing, and every 7 years or so, this temperature goes up by 100 degrees Celsius. And so today we have engines which are 1600 degrees Celsius already there, 1700 degrees Celsius which are also being marketed, and research is going on to take it to 1800, 1900 and 2000 Kelvin. Sorry, Celsius. So what is, it's a lot of effort, very large research teams work on this, but the whole idea of doing that research is what we have just learned in the Carnot cycle, that we want the efficiency of this system to go up. So although we are not directly every day working with the Carnot efficiency and doing this calculation, this is the basic driving force for all of research that is happening here, and what is also happening on fossil-fired power plants. That is, for 565, the idea is to take it to 710 degrees Celsius. When we do that, our efficiency goes up. For the same power output, we need to burn less fossil fuel. Because of that, the carbon footprint is less. We make the power plant a little more eco-friendly. And so climate change is now the issue where efficiency is being re-looked at very seriously, and things which were not done for 20, 30, 40 years are now being done here. Whereas in aircraft engines, this has always been a trend and still continues. Okay, there are some questions here, so let me take those first. Why Carnot cycle is irreversible? No, sorry. Carnot cycle is the only thing where everything is irreversible. I said no irreversibilities. So ideal means this is reversible. So there are no internal losses of any type in the Carnot cycle. That's why it is the most efficient cycle. Okay, why is it not possible practically? Well, practically it is just not possible. Simply because first, if you want to do heat transfer over a very small temperature difference, you need very, very huge machines. That's not feasible economically. Even the engineering becomes very difficult. And no matter what you do, friction will always be there. So that is going to be an irreversibility that is there in the real world. When a fluid moves in a pipe, there is a pressure drop. That is because of frictional drop. So you cannot ever get rid of all these sources of irreversibilities. Processes have finite rates of change, so they are irreversible. So we just cannot get rid of them. There is no hope. Okay, so there is a question that has come up. What is a Carnot cycle? Okay, so let's take that up now. So I have been saying there is a Carnot cycle. So we have seen that the Carnot cycle has to have at least two processes. Okay, how to make a Carnot cycle? So there has to be two processes. First, there is a reversible isothermal heat transfer from the source. This is one process. That means during this process, the working substance temperature is just slightly less than this, practically equal to TH. That means during this process, the temperature of the working substance cannot change. Then we said that there has to be a second process here, which is this heat transfer. So we have here reversible isothermal heat transfer. So this is plus QH with a TL temperature sink and dumping some heat QL. And the temperature of the working substance when it does this is almost equal to TL. Two processes are required. And now we want to complete a cycle. The thing is, the fluid in this state is at TH, fluid in this state is at TL. We just cannot have this directly go into this, because then you will have something where hot fluid mixing with a cold fluid, it immediately becomes irreversible, not possible. So what do we have to do? We have to take the fluid from this state to this state and do something with this. There has to be some other process. Now we've already put a restriction that the fluid has exchanged heat with either TH or with TL. It cannot exchange heat with any third reservoir. The moment the fluid starts doing something and its temperature starts coming down in this, so this process has to be a process where its temperature keeps coming down. And at any point when its temperature is decreasing, it cannot be in touch with this and it cannot be in touch with this, because you have finite temperature difference between them that will cause irreversible heat transfer. So that's not allowed. Which means that as this temperature is coming down, there should be no heat transfer. So this has to be an adiabatic process. And it is during this adiabatic process that you get a work output. So this is a plus W process. You can put it that way. So we heated it, got it at TH, and then we did an adiabatic process with it in which we got work out, and the fluid came down to a lower temperature, which is TL. Now it dumps heat into the sink and its temperature still remains TL. So it has done this heat transfer. So this is a third process that we have added. No heat transfer, adiabatic work output. And we need now one more process that will take it from here to there. And to do that, we will put up another process and argue the same way that we have to have this process in such a way that as the fluid goes through this, its temperature should keep going up. That's number one. Number two, it should not be in contact with either the sink or in contact with the source. That will make it irreversible heat transfer. So as it goes through this, again this has to be an adiabatic process. And here we have to do work on the system. So we say my plus W, we call this out, this will be in. Adiabatic means that the system does not have any heat transfer with the surroundings. So Q12 would be 0 if it were a cylinder piston arrangement, or Q dot CV will be 0 if it is a flow system. So we need two more processes which are adiabatic, and we said that the Carnot cycle, everything has to be reversible. So this has to be a reversible adiabatic process, and this also has to be a reversible adiabatic process. So now we can put the essential elements of the Carnot cycle together. That we take the working substance in whichever the closed system or open system, where in one process it comes in contact with the high temperature reservoir and gets energy QH. It goes in at temperature TH and comes out at temperature TH. Then we put it through a process which is reversible adiabatic process where you get work out. Then we have a process where it comes in contact with the low temperature sink where it dumps heat, QL is output, temperature of the fluid remains at TL, and then we have another reversible adiabatic process in which its temperature rises from TL to TH without heat transfer. So this is temperature drop without heat transfer, this is temperature rise without heat transfer. So that means only work transfers are possible. So those are the four processes we want: a reversible isothermal heat transfer, reversible adiabatic process, reversible isothermal heat transfer, reversible adiabatic work. Those four processes, if we can get together, we will make a Carnot cycle. And to see how that will happen, we will go a little beyond this and now come across the definition of what is entropy. And that will tell us how the cycle has to be made. There is a question here. Is the overall efficiency of engine more than 50%? Is a question where I don't know what engine one is looking at, because thermal power plants, internal combustion engines are all engines. Well-designed diesel engines operating at steady state will have efficiencies of the order of 45 to 48%. Petrol engines are much lower. And remember, this whole discussion about efficiency that we have talked about is only valid if you have steady state. If the engine is not in steady state, we cannot talk about its efficiency. And unfortunately, that is the reality on the road when you drive a vehicle. Your engine is never in steady state, almost. Okay, but coming back to the question, can we have efficiency of 50%? Well, yes, now we can say the heat engine, which is a combined cycle power plant, we will come to that a little later, where you burn fuel in a gas turbine, get a very high temperature there, then use that exhaust to generate steam and then run a steam turbine. That we are talking of processes that get us up to 60% efficiency, and there is research going on to take it up to 66% efficiency. So burning of fossil fuel, oil or gas, not coal, we have the highest efficiency possible in a combined cycle power plant, which people are talking of getting about 66-68%. That's possible. So that's also a heat engine, although it may be a very big, huge building. Thermodynamically, that is a heat engine, because we are putting in fuel and getting heat and dumping it to the atmosphere. The remaining is coming out as work.